Next up, I'm excited to welcome Tim Ellis. Disrupting 60 years of aerospace manufacturing, Relativity Space is the first and only aerospace platform to integrate machine learning, software, and robotics with 3D metal printing to design, print, and fly rockets in days. Since co-founding Relativity, Tim Ellis has helped change the future of space exploration by expanding the possibilities of additive metal manufacturing. Under his leadership, Relativity developed Stargate, the largest metal 3D printer in the world, which produces Terran 1, the world's first 3D printed launch vehicle, and Terran R, the first fully reusable, entirely 3D printed rocket. Tim is the youngest member of the National Space Council Users Advisory Group, directly advising the White House on all space policy. He also serves on the World Economic Forum as a technology pioneer and has been honored on Time 100 Next, MIT 35 Innovators Under 35, and 30 Under 30 from Business Insider, Forbes, and Inc. magazine. Tim is joined by Alex Wang, CEO and founder at Scale. Alex, over to you.
All right, Tim, super excited to be chatting today about all the cool work that you're doing.
Yeah, thanks, Alex. Appreciate having me on. Excited to share.
So you work on probably, the coolest thing that anyone could work on, which is space. And we're going to talk all about how that intersects with AI over time over the course of the interview. But maybe just to start out with, Relativity Space is probably one of the coolest companies in the world. But I would love to just hear you talk about what you're doing in your own words.
Yeah, of course. So I'm the co-founder and CEO of Relativity Space. So we're 3D printing entire rockets. So we build not only our own rockets to launch satellites to orbit, but we also build the world's largest metal 3D printers and the world's largest metal 3D printing factory. So we're based here in Los Angeles. We have about 1 million square foot factory that I'm in right now. And together with a sister facility that's 120,000 square feet, which is building our first rocket about to launch to orbit from our own launch site at Cape Canaveral. So I founded the company about 7 years ago, and we're now the third largest private space company in the world. So we've certainly been very fortunate to benefit from the first 2 decades of commercial private space. But really, why 3D print an entire rocket is I started as a rocket propulsion engineer working for Jeff Bezos' company, Blue Origin. Where I then ended up being the first user of metal 3D printing in my own rocket engine developments. And then I started the metal 3D printing division. So I got to work with Jeff and the other senior executive team at Blue Origin. I started this metal 3D printing division where we were building lots of parts of a rocket here and there. But then I looked at the entire launch vehicle that Blue is building, which had hundreds of thousands of individual parts. And I really realized that 3D printing was not just a manufacturing technology. It was actually really a new platform and a new way to automate and drive software-defined manufacturing for aerospace, because 3D printing really lets you replace the entire factory with a new system that consolidates many parts together, automates the process because you're stitching these parts together in the 3D printer. So you can really reduce part count, labor count, end up iterating very quickly. And then that's really the big competitive advantage that 3D printing a whole rocket will enable. But what I thought is you have to start completely from scratch, because you can't just take a traditional rocket and a traditional factory and go 3D print something. So it's more similar to Tesla, where they shifted from gas internal combustion engines to electric. Really, it wasn't until Tesla came along and realized that changing the entire factory and the underlying technology was what was required to actually see this inevitable shift happen. And I think in aerospace, 3D printing is really just the holy grail for aerospace automation, with very high complexity but fairly low production volume, relatively speaking.
Yeah, so there's a lot of interesting ideas that we'll want to jump in throughout the course of the interview. Maybe to start out with, how did you find yourself working in space in the first place? I think one thing that I know about you that I don't know how many people know about you is that you used to be passionate about writing. So you are a writer, I guess, and passionate about creative writing, and that led you ultimately to space. I'd love to hear that journey.
Yeah, of course. So I grew up in Plano, Texas. So it's a small suburb north of Dallas. And while there, of course, I was always good at math and science in middle school, high school, et cetera, growing up. But I was really much more passionate about writing and film and just this idea that creativity and inspiration can help drive a lot of meaningful change in the world. So, I probably watched like 2 movies a day at various points in high school. Like I literally feel like I was a huge film buff. I actually dropped out of AP Physics with a perfect grade to join the school newspaper, and I wrote 2 fiction novels in high school, which I never published. I probably will never publish them because I was really not even into sci-fi, and I thought space and the space shuttle and International Space Station was really boring. Like I distinctly remember in I think it was middle school, I went to an IMAX theater where I watched people live streaming from the International Space Station back to Earth as a school field trip. And I was like very confused. It was on NASA TV, which if you haven't watched NASA TV is like absolutely unsexy. There are people floating around, and I just thought like when's lunch? Essentially, like my mind really wasn't blown, but my mind was really blown by, Fight Club and Donnie Darko and The Fountain and all these kind of transgressive, philosophical, kind of gritty, existential films and then books ultimately. And so that's what brought me to Los Angeles. And I went to USC. I originally went there thinking I was going to graduate and be a screenwriter and go into film and kind of follow this trajectory of writing things. I think Less Than Zero is the book that actually brought me to LA. I was just so fascinated by this culture that was here. But then during orientation, I had this kind of big breakthrough where I realized all of my friends that were writers that were older were kind of crazy. Like if you know any writers at all, they generally are sort of weirdly antisocial people at times because you have to work really weird hours. You're only working when inspiration strikes. And I honestly just thought this future of me sitting alone in a desk writing for money and having to be creative for money, essentially, and maybe even having to force it was going to be really depressing and scary. And so then I literally was choosing classes for this honors writing program at USC during orientation, and I stood up in the middle of the class. I was scrolling through the list of majors, and aerospace engineering started with an A and was near the top of the majors list. I was always building Legos and super into space stuff as a kid. So then I just literally decided I was going to be an aerospace engineer in that moment. Like this was not a precognated thing. This was truly like a just random fluke. Like even after freshman year, I almost dropped out of aerospace because most of the classes were on airplanes, which I thought were a solved problem and not that interesting. But then there was a student group called USC Rocket Lab, which was working to be the first students in the world to launch a rocket into space, and that sounded like a pretty interesting mission. Fast forward that winter, I saw my first rocket engine test in person, and it was absolutely the most visceral thing. Like I still remember the feeling. It looked like looking into the heart of a star, and just the air was so thick and soupy. Like the power was just absolutely insane. And so then from that moment on, I thought, well, I want to dedicate my life to using my engineering and math skills to make more of that happen, because that was like freaking inspiring.
Yeah. Well, out of curiosity, what were the 2 novels in high school about? Any
Yeah, sure. So, I guess high level, the first one was a story about just like really religious zealot that went to a Starbucks bathroom and drank hemlock to essentially like kill himself and then go down to hell and box with the devil. So, kind of again very like philosophical. And then the other one I probably shouldn't even talk about. I was super into Chuck Palahniuk and Fight Club and a lot of his other stuff. Which if you know Chuck Palahniuk at all, it's like absolutely kind of crazy. So I don't know if anyone will ever see that stuff.
The first one was pretty raunchy. I like it. It's very philosophical. Yeah.
Yeah,
That's awesome.
exactly.
So now going back to relativity space. So one of the things that you talked about was this idea of software-defined manufacturing and how that how that obviously it's very well suited for the problems in space because they're you're designing these very complex parts that have to work extremely well in sort of like relatively few circumstances, relatively low volume compared to other forms of manufacturing. But I'm kind of like, before we dive into that, I've had a chance to actually tour your facilities and see a lot of this stuff, and it's pretty incredible. But maybe it's not obvious, I think, why what the value of having a software-defined manufacturing loop is for the sort of the space problem. So maybe walk through that for a bit. Like, what is software-defined manufacturing allow you to do that is just impossible in the previous paradigm?
Yeah, sure. No, great question. So I think maybe I'll start with, because I appreciate maybe not everyone listening in has been to an aerospace factory or a rocket factory before and even seen what a traditional one looks like. But really, essentially, if you walk into any aerospace factory over the last 60 years, it looks more or less the same. It's this giant building full with huge pieces of CapEx called fixed tooling. So these are, generally machines that will do one step in the process of building a rocket fuselage or an airplane fuselage. Like maybe one of the machines just bends the sheet metal into a like semi-arc, and then another machine will weld a bunch of those pieces together, and then another machine will take that and form that into a bigger part of the fuselage, and then another machine will put the windows in, and then another machine will do this, on and on. So essentially, every aerospace factory for the last 60 years has relied on giant fixed tooling, which usually costs hundreds of millions to billions of dollars in multiple years to develop and even just get the factory set up. And the problem with that is once you actually build the factory, you also have to lock the design in, because you can't then change the design without changing the factory. And there's so much sunk cost, not just in dollars, but in time and energy and effort. And so the rate of innovation ends up being very slow. So you have these factories that have fixed tooling. They're building products one at a time by hand with hundreds of thousands or millions of individual piece parts. Most commercial aircraft have well over 1 million parts. The space shuttle had several million parts. And so you end up with a very complex supply chain as well, where you have vendors spread across kind of all over, generally all over the United States or all over the world. Part of that is politically, so that you have jobs in every state and you can kind of get congressional buy-in for regulators, sort of in every location. But it also really just requires all of these kind of stacking suppliers. They all obviously are charging margins, so you have margin stacking kind of on each step. And then that really ultimately ends up being this like very slow build process, where using traditional manufacturing, it would not be uncommon for it to take anywhere from 2 to 4 years to build a single rocket from the point you order the first hardware to when it's actually complete. So now, it's probably, I would say, with Falcon 9 getting in the realm of 2 years, give or take. Starship, I think, is trying to push that forward quite a bit, but that is still the best practice by far. If you look at the more traditional launch companies, it certainly takes on the order of 3 to 4 years for the whole supply chain to happen. And so then 3D printing really is a technology that replaces most of that. So now you don't really have fixed tooling. You have a system that just changing software of what the 3D file looks like can build different sizes of rockets. You can actually roll in design iterations and change that. So from version to version, you can improve the product with far fewer constraints and having to retool a factory. You also then are able to merge many parts together. So for our rockets at Relativity, they have about 1/100th the number of parts as traditional. Those parts look very complicated when you look at it. I mean, some of these things almost look organic, like they're built via evolutionary algorithms and kind of looking a little bit more nature inspired, because really that's just letting physics drive the design more. But you merge many of these parts together, and then that gets rid of, when you have a single part that's 1/100th the number of parts as traditional, now you don't have all the purchasing, you don't have all the supply chain issues, you actually don't have all the assembly labor and kind of quality control that needs to happen traditionally under each step. And so you're just compressing and getting rid of a significant amount of the work that you would normally have. And so what Relativity is doing is just building that at scale across an entire product. So instead of looking at a traditional rocket or traditional aerospace product and saying, well, where does it make sense to 3D print? We're instead designing the entire factory and development system around this technology. And once you're 3D printing a whole product, then you're also collecting large quantities of data on the rocket as you're building it. You can then feed that data back into better ways to print and get stronger materials, higher quality, faster speed. And so really the inevitable transition, in my view, is that all manufacturing is going to go into digital and data-driven manufacturing. And that really has to happen because fundamentally machines are just going to be better at building repeatable things with high quality than human beings will. And right now, aerospace is still so manually driven.
Totally. I mean, I've seen some of these designs, and exactly as you're describing, they're like very complicated on the inside. There's all these different tunnels where jet fuel and combustion happens, and it's pretty incredible to see. I think very relevant, this concept of sort of increasing the iteration speed obviously is resonates to a lot of people in software, where obviously you optimize for the iteration speed because that's what allows you to build the best kinds of products. And I think this last piece that you mentioned I want to touch on, which is the use of so with increased iteration speed and as well as sort of increased data from the sort of entire manufacturing process, and the fact that you can tune that process purely through software rather than having to go and rebuild a whole machine or redesign your whole process or whatever the status quo is. This shift enables you to start applying machine learning and algorithms to the process of building rockets. And so I'd love to talk about a little bit about that, because I know that you all are doing a lot of exciting work here, and it's really, really cool.
Yeah, of course. So I think talking about specifically, where are we starting to look at using AI and ML and different kind of data science models. Really the core of it. So Relativity is a company. I think we have about 950 people or so now on the team. We develop our own 3D printers, which are the world's largest metal 3D printers. So going back to the original vision, if we said we're going to 3D print an entire rocket, our long-term vision is to help put 1 million people on Mars. We can talk about that in a minute. But that's our long-term mission and vision. And 3D printing is the inevitable technology required to see a large-scale human presence on another planet. It's a big enabling part of it. And so with that, working backwards, we knew that if we're going to one day launch a factory to Mars, of course, we're still a venture-backed company, like build a big business on Earth. But if that's the long-term North Star, the parameters of success are going to have to be a small, lightweight system that can build a wide range of products with very little human labor or involvement in highly uncertain conditions, and figure out how to improve itself, because we're not going to be able to test everything that could possibly go wrong on Mars, on Earth. And so you're going to need a system that can learn and kind of adapt. So all of those parameters, as far as success goes, to me describe an intelligent 3D printing system. And so we knew that we had to build intelligence into that core technology first and foremost. So that's really where we're starting, is our own 3D printers. So since we also fully develop it in-house, we have about 250 people just developing our own 3D printing systems, software, robot path planning, kind of simulation technology. I would really break that 3D printer development into 3 parts. So the first part is we wrote our own in-house simulation software. So we learned through doing tens of thousands of print hours at this point that we actually need to simulate the print before we press print, because there's a bunch of things that you can't really control for once it's actually printing. So predominantly the biggest thing we do is a big thermal structural simulation, where we actually, so as the robot goes around and deposits this metal aluminum wire where it's melting and then solidifying, it's kind of a thermal structural process where you end up getting warping and distortion because of the heat buildup, and where the heat buildup happens, it kind of warps and moves around. And so we had to create a reverse solver where you actually simulate this kind of warping and time history of laying down material, and then figure out what that distorts into, and then reverse it. So we actually print, like for example, even if you wanted to print a fairly basic shape like a kind of orthogrid stiffened cylinder, you actually have to print not a cylinder in order to get it to distort into a cylinder. And so some of that stuff we found, there are closed form solutions for it to some extent. But that's one piece of it. And then the part where it gets really stochastic and nonlinear is then while it's printing. So while it's printing, we have different thermal cameras, visual spectrum cameras, laser scanners, X-ray. Like there's a whole bunch of sensors that we're really starting to merge together into a essentially sensor fusion or perception layer in the printing. And so that really will then let us currently identify flaws as they happen, but really the goal is to be able to predict flaws before they happen and then figure out how do you eliminate flaws in the future as you predict it based on early warning signs or based on large quantities of data so that the printer learns how to produce fewer flaws while increasing the print rate, improving material strength and quality and surface finish. And so I think, in many ways, a lot of the parameters of success kind of can almost have their independent reward functions where you're able to reward individual kind of scores of positivity on the printing, but then it's pretty nonlinear and pretty cross-coupled. So if you start making better surface finish, it may print much slower. And so you have to figure out like what the right rewards are in order to get better print parameters across all of that over time. And then the last piece is just after printing, we collect a bunch of data on what we got. So that's kind of destructive material samples. We X-ray, we look at what's called scanning electron microscopes, which look way down at the kind of molecular structure of material grains and metallurgy. And all of that really is then fed back into the system to help correlate. So the hardest part right now is actually how do we collect the data and tag it. I think this is common challenge here in AI and ML is how do you actually collect high quality tagged data and then start to use those tags in a physically relevant way to make sure that you can actually build a model. And in our case, how do you get enough data? Because we can certainly get like hundreds of thousands of data points. Like at this point, that's roughly in the range we are. But some of the early kind of standard AI ML models needed tens of millions, and so we were pretty far off as far as how much we could collect in order to affect it. So we're starting to look more at like sparser kind of not needing as many data points to still draw correlations, that kind of thing.
Yeah, totally. Well, it's a super cool problem spec, right? And I think it's like non-obvious to people who are just minding their business in AI, just to think about, hey, you can utilize, techniques in machine learning, artificial intelligence to optimize the manufacturing process, any manufacturing process, but especially for space where you're dealing with, really sort of like the frontier of manufacturing techniques and materials and the conditions that what you build has to sustain and sort of and the ability to apply AI techniques to sort of like on the fly adapt the printing process or sort of the manufacturing process is really, really darn cool.
Yeah, I think I'm just so convinced that software and data-driven manufacturing is going to be the future. When you think of what is the right direction to go in, you have to think, well, what is inevitably true and what's not going to change with time. Like I do not see a world where in the future, whether it's 5 years, 10 years, 20 years, or further, where you're going to say, I want a product with more parts and more complexity. I want a more complicated supply chain. I want more fixed tooling and less flexibility, or I want more hands-on human labor with less information about what's going on. So obviously none of that's going to be true. It's like sounds very obvious, but I think it's a really good frame to think about. And then really it's just seeing, what is the stack ranking of kind of highest bang for the buck of starting to use AI and ML, and then how do you actually do it? Like, because we have a very skilled technician force right now, which helps manually build the rocket. We've gotten rid of a lot of their labor hours on watching the printers, but we still have somebody watching all of the prints, while they're printing. They kind of monitor multiple printers at once right now, which is a big improvement. But really, I think some of the top of mind questions for me is how do we start using human training in these systems where you can actually watch the print and then we build a tool set where they can say, hey, this looked off, hey, this looked good, and then you can start to layer in some of the human elements of things, which I think will be really important part of speeding up the training set and actually making it physically relevant for what we're doing. But yeah, I think manufacturing as a whole, certainly what we're doing, but I think manufacturing as a whole has a lot of potential for ML and AI. And I think, to your point, it's really going to be part of the future. Like, I do not think we will have 1 million people living on Mars unless we have intelligent, reasonably sophisticated AI and robotics to help augment it. There's actually a pretty strong argument in my mind. I disagree a little bit with Elon about an asteroid destroying Earth and that being the reason to go to Mars. I think it's far more likely in the next 100 years humans will destroy ourselves before an asteroid's going to destroy us. But when you think of what makes space travel hard with humans, it's really food, water, shelter, and boredom. So it's the human body and our biological needs that make human spaceflight so much harder. Like the Dragon capsule, launching astronauts is so much harder than just a cargo capsule launching satellites. And so the human part's the difficulty. And so when you look at the pace of innovation, especially recently on AI and ML, lots of breakthroughs, I do not see a world where, I don't know if it's 20 years, 50 years, or 100 years, but I don't think it's longer than that time period where intelligent AI and robotics go into another planet, because it is only a few minutes away at the speed of light to send more new updated information, and for robots that don't really have those things that make space travel hard. I think that's far more likely that robots and AI will be the ones that actually are exploring outside Earth in the long run. So this is really the golden window of when humans are probably able to do it far better than robots and AI. And once that happens, it's just going to diverge. I mean, it's just going to become significantly worse over time into the future.
Yeah, totally. Well, a lot of fun ideas in there. I mean, I think, and we'll dive into some of them even more. But I think one of the things that you described, which is a thesis that I really agree with, is sort of take the assumptions like, hey, we need to find a way to get 1 million people on Mars, and that means that it's necessary for us to build intelligent manufacturing systems, and intelligent software-defined manufacturing systems, in all likelihood. And I think that. You see this pattern over and over again in space, which is that the conditions and sort of and harshness, frankly, of building in space forces humanity to innovate mechanisms and methods that are sort of just dramatically more that end up being very useful for all of humanity. GPS systems and all sorts of things that were invented as part of the initial sort of space race, and then. So I think that is very cogent and makes a lot of sense, and it also sort of like really makes it clear why we need these intelligent manufacturing systems that are frankly going to benefit all of humanity for all the things that we build and all the things that we make. And then the second idea that you talk about, I want to dive into it a little bit more because I think it's sort of this it's this very interesting idea, which is okay. So if you look at it, like right now we're in this narrow period of human history where we figured out how to go to space, but our automated systems of going to space are not as good as the humans going to space. The humans can deal with all sorts of circumstances that come up, and they can analyze the data, and they can sort of they're much better at sort of exploring space. But then it's at some point in the future, whether it's 20 years, 30 years, 50 years, 100 years, somewhere in the future we get to a point where AI systems are an AI system, an AI basically, space probe or space drone is going to be a better system to explore the universe. It'll deal with all the unforeseen circumstances that'll come up. It'll be able to process all the data and just send that data back to us. and then we'll get, the end state is that we have, hundreds of thousands or millions of AI-powered space drones going around and sort of exploring the cosmos on humanity's behalf. Is that kind of what you imagine?
But it's pretty much it. Actually, there's a concept that you talked about there at the end called a von Neumann probe. So it's this guy, von Neumann, he kind of popularized the idea, but it's essentially the idea that the kind of end state for human exploration of the solar system and beyond is going to be autonomous, self-replicating spacecraft that can essentially land anywhere and then build more of themselves and kind of grow exponentially in order to just continue, going on and so forth. So that's kind of there is no faster way to explore the solar system in the long run than that. There's a dark side to it. It can be a doomsday scenario where these things kind of go out of control and just consume, most of the known mass in the universe, just building more and more of themselves. So it's a little bit of a crazy, gray goo sort of apocalypse scenario. But look, I think if we get to that point, we've also, as humans, done our job too well, because that's going to be so hard to actually execute in reality. So I'm not super worried about that right now. But yeah, I do think that essentially has to happen if this future is going to exist. And by the way, I'm a huge fan of SpaceX. Honestly, they're the reason I started Relativity. I was working at Blue Origin with Jeff and senior team. Ended up, of course, going to USC. So I had a lot of friends that were here in Los Angeles working at SpaceX. They were 13 years old at the time, and I was really inspired by watching them land rockets and dock with the International Space Station when I started Relativity 7 years ago. But they were still the only company in the world that had this long-term mission of making humanity multiplanetary and going to Mars. I thought that was quite shocking, actually, when you think about it, because 13 years of what is, in my opinion, some of the most inspiring once-in-a-generation success, and so dominant in their success, did not inspire anybody else to start something that was aligned to the same vision and go after it. By the way, Relativity is 7 years old, and even we're only the second company to have this mission of going to Mars. Until very recently, we partnered with Tom Mueller, who is the co-founder and CTO of SpaceX, and he started his own company called Impulse, and we have a joint mission now with them where we're going to launch a payload to Mars on our first launch of our new rocket, Terranar, which is fully reusable, and that one's now in development. So yeah, it's kind of an interesting lesson as well that I don't know if I've seen as much in software. Usually there's lots of fast followers, or there's lots of companies that are trying to do the same thing. Of course, it's very hard to come out on top as the one that's really leading it. But in space, it's just been very fascinating that it's not a guarantee that there's people that even emerge to want to do something ambitious. So I am really hoping that by building a better tool set where the cost of trials, the cost of building a rocket, the cost of building a rocket engine or a valve or a turbopump or any of these components with 3D printing and with more advanced manufacturing means the cost of trial, both in time and in dollar resources, is so much lower that then we can increase the pace of iteration, which I've personally found through testing and developing lots of rocket engines and other hardware. Actually, the number one predictor in my mind of success is pace of iteration. If you can iterate and build and test at a far faster pace in hardware, you will get to a much better end product more quickly. I think there's some fascinating stories on this. One that resonates with me, and I tell our team all the time, is there was a study where an art school professor kind of split their class up into two groups and gave them an hour each to make clay pots. So one group, he said, you need to make as many clay pots as humanly possible. You're going to be judged on how many you made at the end. The other group, he said, you need to make the highest quality clay pot possible. You're going to be judged by how perfect it is at the end. Go. And then at the end, of course, the groups did their thing. Like the group that was told to make high quality generally made one or two, like maybe they did a practice one and then like the final one to make it perfect. The one that he told make as many as possible was just slinging clay like over and over and made a ton. And what's interesting is then at the end, he told them, actually, I was going to judge all of you just based on quality alone. And the group that he told make as many as possible had the highest quality ones as well, even though they had absolutely no mandate for quality. So I think that's, resonated with me and is pretty fascinating because I think it has shown, at least in physical products, the pace of iteration is really one of the gating factors because you just learn so much more by actually doing it. And, you mentioned there's software analogs there. But I really think that this is the big kind of fundamental thing that AI and ML can help with because there's also such complexity. It's not clay pots. We're building rockets. Like it's pretty nonlinear. It's pretty complicated, and there's definitely at least in the 3D printing like stochastic kind of random flaws and cracks and pores and things that come up and blips and bites, and you kind of have to understand what's going on and then figure out how to train for eliminating that stuff over time.
Totally. Yeah, I mean, there's a bunch of stuff in there that is super interesting. I mean, one is this component that you mentioned around iteration speed being the number one indicator of success. This is something that we believe a lot at scale, and actually you see it, frankly, in in AI systems as well. You train bigger and bigger models with more and more training time, and effectively more and more training time equates to more and more steps in the process of training these systems, and you just get crazy things. We've seen this in the past few years where you just get incredible performance and things that are so beyond what anyone thought was going to be possible in the world of AI. And so I agree with all that stuff generally, and I see this reflect in one of the things you talked about was ambitious. There's not. You're surprised there's not more ambitious space companies out there. And I do think Relativity Space, you have this clear streak of ambition. And it's something that, I relate to at scale. One of our values is ambition shapes reality, which is I would say seems to be something that you agree strongly with. One of the ones that you talk about, right, is like this goal. I mean, two very ambitious goals. One is first just doing a launch to Mars in 2024, which is obviously a big deal. But then the next is obviously the sort of broader mission of getting 1 million people to Mars, which is obviously an even bigger deal. What do you think, just as a builder, an entrepreneur, or whatnot? What do you think are the things that have enabled you to be so ambitious, but also really make such incredible progress in accomplishing that ambition?
Yeah. No, happy to share. I mean, I think as far as why be ambitious, like honestly, it just gets a little more personal as far as life philosophy in general. So I know, obviously we're friends, and you're a young founder of a very ambitious company as well. But I feel like I was just very lucky. I started Relativity when I was 25. I was just very lucky in late high school and then in college to kind of come across this life philosophy that more or less has guided most of my thinking, which is really this idea that no matter what happens in your life, like there's one kind of common end, almost no matter what you believe. Like you're still going to get old and you're still going to die at some point. And that could be a morbid thing to think about, but for me, it's actually one of the most inspiring things, because you really then, if you think from that perspective and you actually kind of project yourself forward in that point in time and then look back on your life, it's very clarifying. Like it actually, for me, gives me the sense that you can't really screw up. Like you essentially, essentially there's nothing you can do to fail truly in life, because it's all gonna end anyway at some point. And so I think that has been a really big inspiring thing to say, well then, okay, like if this is your time and this is really all you have, then why not, isn't it one of the most human reactions to that absurdist situation to just be really ambitious and then figure out like how to maximize experience and how do we see the future happen faster and just make life more of an adventure and more interesting. And so I think, for me, that's always been the kind of core driving underpinning to this. And I think also really just this idea that what Relativity is doing, it's certainly very ambitious. I originally we both started in Y Combinator. So I remember Sam Altman was our partner that got us in, and it's funny. He told me I could tell this story, but he's a big fan of ours now. But it was kind of hilarious. The first office hours, I sat down with him because we told him we were going to scrap our smaller 3D printed rocket, and we were going to do a Falcon 9 sized reusable rocket from the very beginning. Which, to be clear, like as a rocket person, like even building a rocket at all is crazy. And then to 3D print a rocket, which is an entirely new manufacturing technology, and having to develop both simultaneously, was kind of nuts. And he essentially said, now you're wanting to do a Falcon 9 size rocket, like you're just like completely insane. Already you have to choose, are you a 3D printing company or a rocket company? Because you're taking two kind of simultaneously ambiguous and ambitious development paths and then stacking them. But actually, I didn't listen to his advice, by the way. Freaked this out for a second there, but we didn't listen to it. We stuck with our North Star vision, which really has not changed since we wrote our YC application, which is kind of crazy. But yeah, we stuck with it because it's actually the synergy of building both at the same time that was the breakthrough. Like really, people have been building 3D printers, even metal 3D printers, for the last 2 decades. This is not a super new technology, but the problem is people have just built the printers. Or just built the products, and they haven't built both together. And really, 3D printing is a new tech stack with a new operating system that really needs to be wrapped around it from a development, analysis, quality control, materials perspective. And so it's kind of inseparable from the product itself. And so they need to be more closely linked and intermeshed. And then you don't have to convince people to use 3D printers because that's a really high customer adoption friction barrier. And so essentially, selling a printer is convincing somebody to throw away all of their existing designs, all of their existing factory capex, and all of their existing technical know-how, and probably swap out part of their team, frankly, with a team that understands 3D printing. So that's a really high barrier to entry for selling 3D printers. Versus if you go one step up in the application layer of 3D printing and build your own end products, now all of a sudden you don't have to convince anyone to use printing. You're just using it yourself, and you're selling them a service. In our case, we launched telecom and other satellites to Earth orbit as a service, and we have all of the steps in between that get a customer to that successful endpoint. And so essentially, they don't even care that our rockets are 3D printed. They just care that it works and it's successful. So I think back to your question, some of it is just really being open-minded with understanding, why have things not worked, and just kind of absorbing that. But I think more ambitious companies are actually more likely to succeed. Ironically, it's much harder to pull off and execute. But then I think the kind of give a damn factor is much higher. Like people actually care to see this mission and vision happen versus something that feels more small or incremental. So I think you end up getting pretty highly talented people to want to work on problems that are impactful and meaningful. I think SpaceX and Elon have actually been a really good example of this. They have the biggest vision. And so I think they've been able to attract a lot of the best people. And of course, great work comes from having the best people, especially in industries like ours where, talent is a definite competitive moat. Just because a lot of the skill sets to get our product to work, there's single-digit people in the world that know how to do it. So you got to be able to get those people. Yeah,
totally. I mean, this relationship between sort of ambition or vision and sort of feasibility is there's this great blog post, I think, I actually don't even remember who exactly it was by, but it talked about this exact relationship where it's sort of like the more, ironically, at some points in the sort of curve, the more ambitious you are, the more feasible your idea becomes, because all of a sudden it becomes a sort of a rallying cry for other ambitious people who want to sort of accomplish the impossible. And that sort of critical mass of talent gives you the ability to actually accomplish the dream, which is just such an interesting phenomenon of humanity in general. The original space race, I think, is a great sort of example of that. I wanted to close as a student of business. I think one of the really interesting things that has happened in space recently, in particular, has been the sort of concept of space as a platform. And by that I mean sort of obviously, SpaceX originally a launch company, and launch is obviously one of the big sort of problems in space, getting stuff to space in the first place. But then with their release of Starlink, and this is something we've talked a little bit about, like it's become obvious that there's more industries and more businesses to be built on top of space as an underlying platform. And I know that this is well aligned with sort of your ambitions at Relativity Space, is like, how can you build out, more and more sort of verticals or businesses on top of the core launch business. And I this is something that we talked about a bit ago, and it's just a really interesting thing to sort of like dream about. What do you think the opportunities that are really on the horizon for space as a platform?
Yeah. So I think worth pointing out. So the overall space economy, in very rough numbers, is around 450 billion a year in total kind of economic output. So it's actually quite a big industry. By far, the biggest fraction of that is in telecom, so telecommunication services from space. So a little bit about how that works. Of course, I think everyone's logged on to Wi-Fi on an airplane and seen that it's very slow and not very reliable, or use internet on a yacht or something like that, or in the middle of nowhere and it's not so good. That's predominantly been because those telecoms are coming from what are called geosynchronous satellites. So they're the size of a school bus. They're very far away from Earth's surface because they have to rotate kind of once every 24 hours, staying over the same spot over Earth to provide a service. But then because of the speed of light and how far away they are, the latency is several hundred milliseconds round trip, and the throughput kind of like megahertz per unit area you can hit is just fairly, fairly small. So that's the old model. What's shifting is now there's mesh networks of interconnected telecom satellites. This is what Starlink is. Amazon Kuiper has a competing system that they're developing. There's been a lot of recent announcements recently on direct to cell. I think this is probably the next big growth area, which is pretty transformational for the industry. So instead of just providing direct telecom to an antenna or a dish similar to what Starlink is doing, or cell tower backhaul, or military communications globally, which is what a lot of kind of satellite telecom networks have done, in addition to yachts and planes and dish TV and kind of TV systems or Sirius XM radio. I think the next big one is definitely going to be directly interfacing with Android, iPhones, Huawei, like whatever kind of devices that you have. And that's going to do a few things. So the first is, of course, emergency services, like hurricane takes out all terrestrial infrastructure, but there's no cloud cover anymore. You can send an SOS message to your family or tell them you're safe, and kind of low data rate, things like that. But I think using smart engineering and further improvements of satellite technology, I think it's physically possible that you actually get more of a broadband-like experience from space direct to cell signal. And what that's going to do, of course, it kind of unlocks a lot of being outside of city centers, being outside of traditional cell networks. As we have more autonomous systems, whether it's autonomous driving or delivery drones or robots, etc., having multiple kind of networks that then can act as a kind of, instead of having 1 sigma availability, you have 3 sigma or 5 sigma or 7 sigma, like whatever the reliability requirements are. Having kind of differentiated network ability is really going to help improve that. Satellites are pretty well placed to go globally, as far as global coverage at a fairly quick basis, instead of having to set up fiber and cell towers or other kind of systems globally. It's still true that there's several billion people in the world that are not connected to the internet. I think from a human optimization perspective, I don't know what the exact numbers would be, but if there's 3 billion people not connected, I would guarantee you there's probably like literally tens of thousands of actual geniuses that are just not really connected to the global ecosystem and information systems in order to help improve and solve difficult problems like climate change and other sort of things that face upcoming generations. So I do think this idea of unlocking intellectual capital and also enabling autonomous systems, better data transfer, better connectivity is really going to just provide a lot of leverage in space. And I think there's going to be opportunities for AI ML just because of the complexity of a lot of those systems. Certainly the quantity of data that we're going to also start pulling off of those systems. I think you're going to start to see things like Starlink do hosted payloads. So, things like adding cameras and sensors to actually collect data, since you're already launching all of these satellites and they're providing telecom services, I would not be shocked if they start layering in other sensors to just start to collect data on a much larger scale, and then use that to help improve weather predictions, insurance, like hold countries accountable for emissions and other things, and just generally have more data transparency and understanding of the world that we're living in.
What are your thoughts on space manufacturing?
Yeah, so I think space manufacturing for me is probably the second one. So I think space manufacturing does need to happen at some point. I actually don't think, though, space manufacturing is going to be largely used for things back on Earth. It's possible that there will be some niche applications. Like I know pharmaceuticals are actually somewhat interesting in space. I know drug discovery and research and kind of virology is interesting in space because in zero gravity, different viruses and bacteria actually behave quite differently, and some of them get much more aggressive and replicate faster. And so there's some interesting small scale stuff there. But I think the in-space manufacturing for things in space is actually going to be the big breakthrough. So once you can build, like it makes sense. Like every sci-fi movie essentially has this, where you're building giant spaceships going somewhere else, and almost all of them, like whether it's Star Trek or other places, are actually built like in orbit, because being able to actually build things that are large enough where you don't have to launch it from Earth's atmosphere, like you can just fuel it in space and go. Same with even the satellite kind of direct to cell stuff I was talking about earlier, requires really huge high gain antennas, and you're going to need to manufacture those in space at some point, because you just cannot launch like there's some physical limit where the antenna has to fit in the rocket. And even with a Starship sized rocket, which is absolutely huge, like there's still a physical limit. And so if you could manufacture and construct in space and get around those limits, you'll really unlock quite unique capabilities. But that's, again, more autonomous systems. I think they need more intelligence in what they're building. Like, currently, I would say the best technology is probably the Mars rovers. There's some military stuff for sure, which I won't talk about. But the Mars rovers from a civil perspective, and they still require people back on Earth to make decisions after looking at data, which takes hours and sometimes days. And often they're looking at basic things like, there's a rock, how big is it? Like, should we go over it, or should we go around it, or is it going to cause damage? And obviously all of that is quite slow. Like, most Mars rovers haven't driven very far once they get to the surface. But if we built in more intelligence and more, similar to self-driving car technology into that, and had ways to make better decisions and identified, what to do, then we would actually explore quite a bit faster. So I definitely think this is going to be a core part of the future for the space industry.
Yeah, super exciting. Well, on that note, talking about the future of space, thank you so much for this amazing conversation, Tim. We talked about a lot of really interesting topics, and I continue to believe that Relativity Space and what you're working on is some of the coolest tech happening in the world right now. So thank you so much for the great combo.
Awesome. Yeah, sounds good, Alex. And obviously big fan of scale as well. You guys are awesome.